All right, hi everyone. We're continuing our discussion of the second law of thermodynamics, and specifically today we'll talk about calculating entropy changes. It's covered in Atkins 3b. In the previous video, I showed you this slide. We were talking about the Carnot cycle, this theoretical way to talk about the efficiency of an engine. And what Carnot's big insight was there was a quantity, Q divided by T, which looked like it was conserved for the whole cycle. That is, that if you added it all up, you got a sum of 0. And that's important because it suggests that whatever this is a state function, right? Like energy. And that'll be our starting off point today. Let's define a quantity entropy. Give it the symbol S and tentatively define it as delta S equals Q divided by T. We're now going to calculate that for a couple of simple cases. And here are the first two. So the first is an isothermal reversible expansion of an ideal gas. The second is an isothermal free expansion of an ideal gas. Remember that the free expansion means that the external pressure is 0. And so what's important is that both the initial and final states here are exactly the same. So if I were to sketch it on a PV diagram, here's the isothermal. Oh, man. Isothermal, right? The second one, I lost my pen, is the same one, but I'm going to draw it as a dash line, right? Because the external pressure is 0, it's the free expansion. So the initial and final states are the same, but the path is different. Okay, here's my definition. Delta S equals Q divided by T. Well, remember, this is an isothermal process, so delta U is equal to 0 for an ideal gas. This means Q is equal to negative W. If you remember your equations for work for a isothermal reversible expansion, it looks something like this. Q equals nRT natural log Vf over Vi. When I calculate Q divided by T, then you get nR natural log Vf over Vi. Over here, right, again, delta U is 0. This is an isothermal process. Q is equal to negative W. Work, remember, is minus P external dV. And because P external is 0, work is 0. Q is 0. Q divided by T is 0. And this leads to a problem. We've considered two different changes. The initial and final states are the same. It's just the pathway that's different. And what this means then is that because we have two different answers, either entropy isn't a state function or our definition is wrong. And so we need to think about that. And it will turn out that the easiest way to resolve it is to consider some third path. So PV, here was the initial. Here was the final. Why don't I consider some third path between these? And specifically what I'm going to do is do this. So I'm going to do it in 2 steps. where the first one is an adiabatic cooling. I'm going to go from some hot temperature T1 to some cold temperature T2. And then I'm going to do a constant volume heating until I get it back to T1. Okay, if I get the same answer, that will tell me something. So here we go. Step 1, which was the adiabat. Remember that for an adiabat, Q equals 0. Right? Therefore, this delta S is equal to 0. That's why I picked it. Makes my life easy. Step 2 was the constant volume. And in order to move forward with this one, what I actually need to do is use this sort of mathematically rigorous version of the above equation. It's called a defining equation. And it's basically the infinitesimal version of what we previously saw. dq divided by t. If I look at the first law of thermodynamics, the infinitesimal version of that is written here, dq plus dw. This is a constant volume process, so dw is 0. du is equal to dq, constant volume. And we saw before that this was cv dt, right? All right, I plug this in. ds equals cv dt over t. And I integrate. Delta S equals cv. This is a dt over t, so that's natural log t1 over t2. It's looking close, although this is different than what we had initially had. This is in terms of temperatures. We need something in terms of volumes. What you'll remember for an adiabatic cooling is that T final, or an adiabatic expansion, T final over initial equals V initial over V final to the R over CVM. If I plug this in to here, you get CV natural log V final over V initial to the R over CVM. You'll notice I switched these, but that's because T1 and T2 are switched. Right? I'm going to bring this down equals CV N R over CV natural log VF over VI. Cancel, cancel, equals NR natural log VF over VI. We just got the same answer that we got before. And so what does that mean? It means that entropy is looking a lot like a state function. Right? I get the same answer regardless of the path that I use to calculate the change. Right? What's different about these is the nature of the path. And so it will turn out that my equation for entropy is wrong. If you're someone who's taking notes, write these equations in your notes. Delta S is equal to Q reversible divided by T, or ds equals dq reversible divided by T. Here's what I want to tell you. Entropy is a state function, like temperature, energy, or pressure. The change in entropy only depends on the initial and final states, not the path between them. However, to calculate entropy, you have to choose the heat that would be transferred along a reversible path, even if that's not what was taken. Okay. So this all sounds a little abstract right now, but I'm going to try and give you some specific examples that'll help, and as we move forward, it will start to make some more sense. Because we can choose any hypothetical path, right? We commonly divide them into 4 different types, and they're listed here: a reversible isothermal expansion, reversible constant volume heating, reversible constant pressure heating, and a phase transition. So I'm going to quickly try and derive some results and then summarize them for you. Reversible isothermal expansion on a PV plot that looks like this. We already calculated this one, and I'm not going to derive anything. I'm just going to put this answer in. It's natural log VF over VI. That's the answer for the change in entropy for a constant volume heating. Give me 1 second. Hey, can you guys shut the door? A reversible constant volume heating. In a PV plot, this would look like this. It's a constant volume, process. Imagine those lines connect. There we go. ds equals dq over t equals cv dt over t. Delta s, if I integrate both sides of this, it's cv natural log tf over ti. Reversible constant pressure heating. Pressure is constant. I'm going to cut right to the chase. In this one, you get an equation which looks really similar. It's Cp natural log Tf over Ti. Because it's a constant pressure, we have Cp. Last but not least, phase changes. You may remember this from a Gen Chem class, but there are these things called like cooling curves. So what you do is you plot temperature versus time. And you start with some solid and it cools. And then it changes to a liquid. So we're talking here about a solid to liquid transition. And what happens to the temperature at that phase change? Well, it stays constant, right? And then the liquid starts to cool. Okay. The important point here is that temp is constant. During phase change, right? This is usually called the transition temperature. And so that makes my life a little easier. dq divided by t, I integrate both sides. Delta S equals q divided by t transition. And the question is, what quantity do we associate with heat of a phase transition? Well, that's delta H. So the equation for the change in entropy of a phase transition is delta H of the transition divided by its temperature. In summary, here are 4 equations that we just derived for phase, for changes in entropy. Right? Entropy is a state function. I have to calculate the change in entropy based on the heat transferred along a reversible path, even if it is not reversible. You can analyze this, and what you'll see is that entropy, which you probably commonly associate with randomness, will increase with all of the kind of variables that you think. For instance, temperature. Right? As temperature increases, entropy increases. Disorder. In general, solids are lower than liquids and are lower than gases. Or volume, right? If temperature is constant, the volume increases. System gets more spread out and harder to locate. So there's going to be some good example problems for you. Look at them, and I will see you next time, and we'll talk a little bit more then about how we relate all of this to the second law of thermodynamics.